Alright, so this is the first video in thermochemistry or thermodynamics, which is basically the study of energy in a system. So for this video, we're just going to be doing some basic vocab and then also a basic heat problem. So when we talk about heat energy, we need to talk about kinetic energy. Kinetic energy is equal to 1/2 times the mass times the velocity squared, and this is of a molecule. So if you increase the temperature, you actually do increase the kinetic energy, which is also going to change the velocity. So if you increase the temperature of a system, so let's just say it's a container of gas molecules, you're going to increase the kinetic energy. So you're going to increase the movement of those molecules. Well, when you do that, you also increase the velocity. Not to get this confused with the mass concept. So if you have a lighter molecule, that will have a higher velocity. So if a molecule has a higher kinetic energy, it also has a higher velocity. However, if you have something that's heavier, the velocity is going to be slower. So the kinetic energy will not be much different in a lighter molecule. So basically, if you have containers and they're asking you to compare the kinetic energy. So if they're all at the same temperature, so let's say that's like 300 Kelvin. If they're all at the same temperature, then really they have the same kinetic energy. Now if you have helium versus argon, argon's heavier, this will have a slower velocity than helium, but if they're at the same temperature, their kinetic energy is relatively the same. Okay, so you need to keep that in mind. Temperature impacts kinetic energy. It can also change the velocity, but if it's asking you to compare the kinetic energy of heavier molecules, if it's at the same temperature, the kinetic energy should be the same. Now if you have one that's at a higher temperature, that will be different. But if they're at the same temperature, kinetic energy is going to be the same. All right, so when we talk about heat energy is the result of moving molecules. So if you have something that's hot, well, the molecules are moving around a lot, and then if it comes into contact with another system that's not as hot, those molecules start colliding with each other and they transfer energy. So eventually, after enough collisions have happened, the heat transfer will stop, and the heat is transferred through the motion of molecules colliding with each other. So eventually we come to an area or something called thermal equilibrium. So that's when both the systems are at one temperature and there's no more heat being transferred. So if you have something hot come into contact with something that's cold, it's going to transfer energy until it meets thermal equilibrium. Now, heat energy can be measured in joules, kilojoules, or calories. All right, specific heat capacity is the amount of energy required to raise 1 gram of a substance by 1 degree Celsius. Because of that, it's measured in joules per gram degree Celsius. It can also be measured in kilojoules per gram degree Celsius, or this could be moles, and this could be also Kelvin. So this one right here is in joules per kilogram Kelvin per Kelvin. All right, so this is an intensive property. So no matter how much I have of that substance, it will always be the same. So it can actually be used to identify a compound or an element. So if I have copper, copper will always have a specific heat capacity of 381. So that means it takes 381 joules to heat up 1 kilogram of that substance by 1 Kelvin. Now, if we look at the specific heat capacities of these elements and these compounds, well, the higher it is, the more energy it takes to heat up 1 gram of that substance by 1 degree Celsius, or in this case, Kelvin. So the higher it is, the more energy it's going to take to heat something up. So water takes a great deal of energy to actually heat it up. It's one of the reasons that a pool will stay cold until probably about June, because it needs to absorb enough energy to actually get to a relatively good temperature. Okay, so a calorie. When we talk about calories, that's actually the amount of energy required to heat up 1 gram of water by 1 degree Celsius. So a calorie is actually the specific heat capacity of water. So it takes it takes 4.184 joules to heat up 1 gram of water by 1 degree Celsius, and that amount of joules is equal to calories. Now, sometimes you'll hear just heat capacity and not specific heat capacity, and then that's just the amount of energy required to raise the temperature of an object by 1 degree. This is going to be different depending on how much you have. So you could have 5 grams versus 50 grams. It's going to take a lot longer to heat up 50 grams than it is 5 grams. So this is not dependent on the identity, but but how much you have, rather. Now, if you have heat in a substance, those molecules are going to be colliding around with the container, with each other. So if you actually place molecules in a piston, it can actually do work. So heat is energy, so energy is always conserved. Well, sometimes that energy can actually be transferred into something useful. So if we put gas molecules in a piston and we start to add heat energy to them, those gas molecules are going to start to move around more, they're going to start colliding more, and they can actually start to push the piston up. So when that happens, the heat energy is actually transferred into work. So work is equal to the pressure of a gas times the change in volume of that gas. All right, calorimetry is a technique. So just like we use gravimetric analysis to isolate a precipitate, and then we use that to analyze different things about that precipitate or whatever we started with, calorimetry is a technique that we measure energy changes in a system. And with that, we can actually determine a specific heat of a metal or an object. We can determine different things about a reaction in terms of heat energy. So basically what happens is that we have an object, or sometimes we have a reaction and that causes heat, or we heat up that object, and then basically that heat energy is transferred into a bath, and it's usually water. So we transfer energy from a hot object or a hot reaction, and that goes into some sort of water bath. Usually it's water. And what will happen is that object will start to lose energy, and then the water will start to pick it up. So it's losing energy. So an object is losing energy, or a reaction is losing energy, while that water gains it. And then we can actually measure the energy that's gained in the water. Now in calorimetry, this is what we usually use to make all these measurements. So we have, basically we have some sort of apparatus that is highly insulated, and then there's a water bath of some sort, and then sometimes there's another separate container where the reaction happens, or we put an object. And basically the whole deal is you want to keep it very insulated, so you keep all the heat energy conserved. So this way, the heat energy lost by an object or system is gained all the way into the water, and we don't lose any into the atmosphere. All right, so when we measure heat energy, we use Q as heat. Sometimes you'll also see it as delta H, which is really, it's the same thing in most contexts. So if we see Q or delta H, we're talking about heat energy. So the heat energy is equal to the mass of an object multiplied by the specific heat of that object times the temperature change. So anytime we see this, it means change in, which means the final minus the initial. It's always final minus initial. All right, so let's do a problem. So propane is the gas that's commonly used in gas grills. A sample of propane with a mass of 44 grams is completely burned in oxygen, and in that process it releases 2002 kilojoules of energy. This chemical reaction is brought into contact with a water bath, and there's a transfer of energy. Assuming the specific heat capacity of water is this, and that 100% of the energy is transferred to the water, answer the following questions. Okay, first of all, if it says 100% of the energy is transferred, that means all of the energy lost from the propane is transferred into the water. We don't lose it to the atmosphere. All right, so in which direction does the energy flow? Well, we are burning propane, and then it says that it releases 2002 kilojoules of energy. So if it releases energy, then that means that we are removing the energy from the propane, and then we are allowing that energy to be absorbed into the water. So it moves from the propane reaction into the water. All right, so now we want to calculate the change in temperature of 20 kilograms of water. Okay, so you have this problem in front of you. I'm going to use a blank screen for this. All right, so we're going to separate all the information out. So we're going to take out all the information. We know that we have two objects here, so I'm going to separate the information like this. I'm going to have propane in one, and then water in the other. All right, so if I read the problem, it says that we have 44 grams of propane. So that's the mass. And it also says that it releases 2002 kilojoules of energy. So energy would be Q, but since it releases it, we actually have a negative Q. So anytime that I have heat energy and it's being released, that means that it's being taken out of the system, so it's negative. All right, now for water, well, it tells me the specific heat capacity, which is C. So that's 4.200 joules per gram Kelvin. All right, be very careful about your units here. It also tells me the mass of the water is 20 kilograms. Oh, not kilojoules, kilograms. And it's asking for the change in temperature. So it wants to know how much the temperature will change by. Well, if I go back and look at the problem, I also know that in this system, this is being lost, the energy in the propane is being lost, but the water will gain it. So water is going to be gained here. So it's actually going to be 2002 kilojoules that I have gained. And that's going to be positive because water is gaining it. All right, so knowing this, I'm trying to find delta T. Well, heat energy is equal to MCAT. So Q, I have my mass, I have C, so I can find delta T now. I could also be finding the initial temperature or the final temperature. I just have to be given one of the two. All right, so I have to go back and double check my units, make sure everything matches C. So I have joules here, kilojoules here, so I'm going to convert that to joules. All right, so that's going to be joules. There's 1,000 joules in 1 kilojoule. And then also grams. That has to be converted to, kilograms has to be converted to grams. So 20 kilograms, well, there's 1,000 grams in every kilogram. All right, so now that matches, okay. So now I'm just going to plug everything into this formula to solve. Okay, so Q is equal to this. I have 20,000 grams. My specific heat is 4.2. and delta T is unknown. So I'm going to plug everything in the calculator and solve, and my delta T should be equal to 23.8. Now, to figure out the unit here, well, I know my kilojoules will cancel, my joules will cancel, my grams will cancel. I'm going to be left with Kelvin, which is going to be my unit here. So if this is combusted and I have a water bath and all the energy is transferred, the temperature of the water will go up by 23.8 kelvins. All right, so now let's see, is the combustion of the propane an exothermic or an endothermic process? Well, if the propane releases energy, then that makes it an exothermic reaction. All right, and that concludes this little section.